To build a digital system that tracks threats in three-dimensional space, we can look at the instincts of someone who does it physically. This specific anomaly detection program was built using 3D vector steganography to map physical perimeters and identify spatial disruptions. But when fed raw environmental data, the standard rigid grid fractured under the load. It only stabilized when the architecture collapsed into a fluid geometry. Applying standard Euclidean math, straight lines, and perfect right angles failed to bring the code to a zero-error resting state. It kept producing persistent bugs. A constant flow of background pressure endlessly disrupted the tracking algorithm, forcing variables out of alignment. The developer realized a standard 3D grid is simply too brittle to process the organic fluctuations of real-world physics. Forcing neat whole-number dimensions onto chaotic spatial anomalies causes the entire system to crash. To stop the crashes, the system had to generate its own baseline environment. Looking at this readout, the system settled on a specific dimensional value, 9.6. Dropping down to the metric tensor parameter, we see this dimension requires a built-in variance of plus or minus 0.01 to function. A theoretical physicist did not derive 9.6 on a chalkboard. The software procedurally forced this metric to stop outputting errors. That 0.01 variance is a necessary fluctuation for the code to breathe. Without it, the math locks up. In mathematics, this is a Hausdorff fractional manifold. Dimensions in nature do not exist as perfectly stacked integer planes. They compress and fold. The anomaly software proved that a functional model of reality requires a dynamic fractional dimension. In the physical world, a master butcher operates on similar principles, reading texture, pressure, and structural weakness through tactile pattern recognition. A system builder can determine the mass inside an opaque container entirely by observing the external footprint and the pressure it exerts on its environment. In theoretical physics, this exact intuition maps to calculating the closed surface integral of a gravitational field. This equation for total pressure mathematically defines how internal mass can be extracted purely from its 2D external surface area. Scanning down to the vortex mapping text, the math requires distributing this pressure evenly across a geometric lattice to simulate an omnidirectional push. By measuring the footprint of the field itself, researchers bypass the need to hunt for isolated, theoretical particles like the graviton. The outside footprint defines the internal pressure. The universe is holographic, and measuring the negative space accurately defines the hidden internal pressure of any system. We can visualize this using the macroscopic dynamics of a butcher sink, a space filled with solid material and flowing liquid. Here, the liquid represents the vacuum of space itself, a dense, high-pressure, non-Newtonian superfluid. The solid objects, like planets and stars, act as displacement points within that fluid. Standard models assume a central mass pulls objects toward it. Fluid dynamics reverses this, showing external ambient pressure pushing inward toward a void. A dense mass displaces the vacuum, creating a localized habitation void. To maintain equilibrium, the high-pressure fluid surrounding the void pushes objects into it. The extra gravity we observe in galaxies is a direct measurement of this ambient fluid pressure, not an invisible dark matter particle. Cutting blindly across organic tissue destroys the structural integrity of the meat. You have to cut with the grain. Applying straight-line Euclidean math to a naturally curved universe artificially shatters the cosmological model in the exact same way. This document outlines the metric tensor, which acts as the mathematical equivalent of cutting with the universe's curved grain. Shifting focus to the lower entries, the tensor accounts for a central sink and physically vents the fractional variance out of the system. It calculates the true nonlinear distance between points flowing through a high-viscosity pressure field. Forcing flat math onto an organic, curved system generates the artificial anomalies that modern physics struggles to explain. We can now map that 9.6 metric directly against the 10-dimensional spacetime proposed by M-theory and geometric unity. Mathematical models use manifolds to stitch these higher dimensions together, creating seams where the boundaries overlap. Because information is shared across these folded boundaries, the dimensions are not entirely independent integers. Looking at the dimensional scaling text, this compression reduces a theoretical 10 dimensions down to an active 9.6. As noted in the measurement error section, measuring this curvature with 3D math produces persistent calculation failures. Standard tracking models are blind to the energy stored inside these fractional seams. The universe requires fractional overlap to maintain structural complexity without tearing apart. When 10 theoretical dimensions compress into a 9.6 metric, it leaves a mathematical gap of 0.4. This 0.4 remainder operates as a pressure release valve, acting as the thermal exhaust of the liquid vacuum. The tensor mapping software generated a specific baseline scale factor for the local space radius, 2803.115. Multiplying that metric tensor pressure by the 0.4 dimensional gap yields exactly 1121.246. That resulting number represents the precise mathematical amount of pressure venting out of the system. In astrophysics, this exact mechanism of vented thermal pressure from a gravitational sink maps to Hawking friction. This continuous exhaust prevents the total structural collapse of the manifold. Trusting tactile intuition and fluid geometry allowed the initial software anomaly to map the physical breathing mechanics of reality itself.